guess I graded most of your assignments and so on. So of course I didn't grade the last assignment yet. And I don't think everyone have submitted yet. But if you go to Canvas and look at your current standing, so I think it's like you need how you understand that is that you need that's the absolute mark that you have for the moment. So that will change after homework 5 is graded, and you can rely more or less like that. That is probably your current standing, and know that like, you need 90 points to get an A, 80 points to get B, and so on and so forth. And for the remaining points you can get is basically from the project. Yes, at the moment I make it zero, make it easy. Yeah, the final project is now, yeah, that's the way that that's the thing I want to kind of clarify, because I just because it is very confusing if I don't include that. I mean, if I don't know how to make it, like either I say zero, otherwise you don't see your current standing really, because then they will consider the report or as your current grade, the final report grade. Basically, the final, if you remember the final project, including the basically a proposal is like 40 points, and or like 40%, and 5% is basically the report. And I basically at the moment I just put everyone for the final reports as zeros, just to make it easy for you to know where you are standing. Otherwise, you will get like you will see yourself basically have like 40 points, because almost everyone the report I give, unless you have something really not clear, that most of your reports I get 5 points, all 5 points basically. So, but now your report is basically now I set to zero, just to make it. I think it's like simpler for you to know like where you're standing. Basically, you need you at most you can get 35 points from that. You can get even more. You know, you have some extra credit if you also prepare for video presentation. But know that it's not like you always get like, it's not just you submit it, you will get like 35 points or something like. That's please take a look of the requirement and the expectation, like that's listed in the Canvas. uh and yeah, so anything unclear about that one? um So I guess the only thing I want to point out is like, don't worry about that. Like you see your grade looks like it's very low at the moment because I deduct 35 points basically. But the remaining part maximum is more than 35. Then for the remaining part, like as long as you add it together, it's more than 90 points, you get an A, or if like more than 80 points, a B, and so on. So and I also take a look of your homework. As I said, I can talk about the solution because not everyone have submitted, but I spot like some common mistakes. I guess it's okay for me to just talk about that in general. Just two things. I like to clarify a bit more like for the maximum likelihood map and Bayesian. Like just quickly. So think of like you have some parameter. So basically what's going on like is like you have some parameter you don't know, you want to estimate, say, and you have some observations. Let's say I just call it observations here. And then based on your theta, then you want to predict something else. Predict, let's say like something else, I call it X, something like. So in your homework or something like that, you can think of the observations like you observe two tails, right? And this theta is the probability of the head, and this X is the future, like the third toss, whether it's a head or tail. So this can be like head or tail, right? Now, so basically for Bayesian, or like maybe I start with like maximum likelihood. So the maximum likelihood is I just look at the likelihood. So for a theta, and given the observation, this is basically a likely function, right? I just try to maximize that basically. I try to find the theta that is my chosen theta, my optimum theta, consider with like maximizing the likelihood. And then using this estimated parameter, I'm going to estimate x. So my x, then I estimate x. Maybe I write like XMLE will be just equal to whatever x is parameterized by this theta hat, something like that. And okay, it's a little bit abuse of notation, but I guess it's okay. Or like I put a function of something like that. Maybe like it's a little bit better. So based on this theta, then I will kind of like get my estimate of x hat there. So this is MLE, right? And map is basically just again, you're trying to find the optimum theta there, but you base on your posterior probability. So your posterior will be like that, right? So then again, like my optimum or my estimate, map estimate will be just something like that. Theta hat, maybe I put a MLE here also. So for Bayesian will be just basically difference of Bayesian is like you consider prior, but at the same time you don't just consider one the optimum or like the one maximize your posterior, but you kind of like average out all the possible models there, all the possible features here. So therefore the Bayesian will be like I have my estimated x, my base estimate will be something like my posterior. Basically, I will kind of like for each of the theta I have an estimate, right? Each of theta I have an estimate, but I weighted some all the theta weighted by the posterior probability. So that will be the Bayesian approach. I skim through like most of what you did, like most of you get things like correctly, but I also like see problems like the following, like some of you like, for example, like we have a problem that have two tails. I'm trying to estimate what's the outcome, like the probability of getting a hat like in the third toss, right? And some of you did is like you take the entire thing of observation, so you're trying to maximize like theta TTH, something like that. Let's say this is like to get the map estimate. And this is not right. This is incorrect because this is the hat here is not the observations. Your observation is only the two tails here. This hat is like what you're trying to estimate, right? You want to say like whether the next toss is like really more likely to be a hat or more likely to be tails. And this should not be included in the observations basically. So any questions for that? I just want to clarify this part for the map maximum likelihood, or kind of like summarize this thing a little bit. And other thing I want to mention is that also from your homework, like some of this, I guess maybe I will make it even a question, something like that, like quiz, like, I don't know, maybe, I don't know, maybe this is not like this is difficult to answer, I guess. But let's say I have x given y and z equal to small c here. And let's say if I expand that, I say this is equal to P y x given y equal to small y, c equal to small z here. So my question here is like, oh, okay, I can still put a question here. Is that correct or incorrect? Yes, correct. Incorrect. I mean, this one, this equation, is that correct or incorrect? Is my question clear? I guess it's like, yes, actually, when I first looked at that, I thought it was correct also. Yeah. That's why like, sometimes it's not, it's good not to just remember equations, but also like try to think of like what is the original definition. So this is actually not correct, because you think of like what's like first of all, like what is x given y z here. So this is like expectation minus log p x given y z, right? Or I can write it as a summation like sum over y and sum over x y z, right? And p x y z minus log p x given y z, right? But don't worry about my comma right here. Sometimes I forget to comma, but yeah. So and then now I can write it as a px, right? Px I put a probability of x out, the marginal probability of x out, and then I have like py z given x left here, right? Then I sum over y z here. So this together, when they multiply together, we get back like x y z, right? So I didn't do anything special here. Now you look at that, like what do I have here? This is a h x given. Oh, sorry. Wait a sec. Oh, okay. I'm sorry. Like, I don't want to sum over x here. Right? I want to sum over c here. Let's say sum over z here. P z p yeah, p x y given z, right? And this is a x and y. Okay, now it looks all right. Now you think of that, then this part is a x given y and z equal to 0, small z, right? Because this is basically like what we expect like the thing supposed to be, and therefore like this thing is actually it's just this guy here, right? But then like okay, I continue to expand this thing. Like what do I have? Like I have like
Dr. Cheng?
Yes.
In the summation, shouldn't the probability be
minus that,
x given yz? No,
okay.
the inside the x summation over xy. I thought it should be probability of x given yz to same as the parameter inside log.
Oh, okay. I'm not using that. Okay, I'm not looking this thing to say this is a hx given yc, but I'm looking at this thing like in the sense like when I expand hx given yc, it will be like expand as a hx given y z equal to small c, sum over p, I mean weighted sum by pc, right? So okay, this expansion here, like this doesn't, first of all, like here to here, I didn't do anything fancy, right? Because this I only split like using base rule here. This split pxyc into pxy given c multiplied by pc, right? And then because pc does not depend on x and y, so I can push this as pass some of the summation inside, right? So this from here to here, like that's I didn't, yeah, I didn't treat, basically I didn't put anything special here. Yes, yes. But then I'm arguing like this actually is like supposed to be the definition of this guy, right? Because that's exactly like what we expect. Like if I have x, y, z here, I'm going to expand that. It'll be like look at like each of the different z here, right? And then I weight the sum by like for the probability of z. But then if I continue to expand this guy, then you see that why this definition is not quite right, because then I have I can expand this as like y p y given z, is that right? P x given y z. So basically this I can expand like this way. Now again now because this part does not depend on x, so I can push this summation to here, right? And then I have log p x given y and z. I have minus here. Now this this is apparently what we expect as a x given y is equal to small y and z equal to small c. So this is this guy here. But then you look at that like, therefore like this part here, the left hand side, that's basically equal to this guy, should be equal to like this one, if I use this color, this one, basically this part here, weighted by like py given x, py given z. So actually, if you think of that, it's reasonable as well, because you already given z here, right? So if you think of the original equation here, or like think of like what we originally try to expand here. So we already given z equal to small c here. So when I weighted this guy, I should also condition on this small c as well. So therefore, like I should have, instead of like weighted by like py, I should weight it by like py given z here. So therefore, like the correct equation should be like that. So I rarely write this equation down. So therefore, I did have the same at the beginning. I did the same thing as you guys. I look at that like just like quickly. I thought, oh, okay, it seems something wrong. But then, yeah, this is actually not quite correct. Yeah. So if I like to expand like this should be like weighted by like py given z instead of py. So any questions? So because I see like some of you guys in the homework like basically use this equation here to, but then like if you use this equation but you are not weighted by the conditional probability but instead weighted by the probability, then you won't get the correct solution eventually. Yeah. So and so any questions on that? If not, I will just move on. So yes,
Professor, I have a question. Can you
yes,
show the screen, previous screen?
yes.
So at this last step, you have also taken this expectation of z, p of z. So this should, do we not need this in our expression on the top? So I'm trying to understand where this is gone. The first in the last step, like
Yes.
last line, the first term.
Yes.
Before this, the expectation on Z.
Here.
No, on the last line, the first one you have written.
You mean this one, or this one, or this one?
Yeah, this line.
Okay, yeah.
You have written on the left side after equal, you have written expectation of Z P of Z, right?
Yeah, I'm saying this is equal to like H is given Y equal to Y, Z equal to small z. Yeah. So you have a question of this guy, or like
Left of this.
This one? Yeah.
Yeah, more left.
Or this one?
Start. Yeah. Where is why we are missing this in the main expression?
Oh,
Because
you
when we
mean
try
here?
to
You mean here?
when we try to expand x, yes, when we start expanding this x y given y into z, so we had this expression of expectation of z on p of z, but why we are not having it on the top?
Okay, we expand. Okay, this is different. Like you see, I start with this these two are not the same thing here. I mean, these two are not the same thing. You see, so this one I already condition on small c, right? But this one is like does not condition on small c. So
Okay,
therefore, this
yeah.
one should be yes. So you see it now?
Yeah.
Okay.
Okay.
So so okay, I guess I will move on then. I guess you okay. So what I'm going to do, like today, what I'm thinking is I'm going to talk about two things. One is I want to talk a little bit graphical model. Just in pretty general case, but I guess it's actually I think like it would be useful to some of you guys. So of course, I first thing you saw these models before, but you probably never gave too many thoughts about those. So and then for the second half, I'm trying to talk something about MCMC. So that's basically what I'm trying to do today. So to start with graphical models, they're typically like there are actually three most common models. So you have like directed acyclic graph. So this is directed acyclic graph. So this is also known as a Bayesian network. Then we have like undirected graph. And we have fat graph. So let's start with the Bayesian networks. So this is actually, I think it's probably the most intuitive. So it's like in the sense it's a directed graph, as the name suggests, it's a directed graph, but also it's a cyclic. So by the way, like the purpose of these graphical models are we are trying to intuitively capture or like visualize the relationship or like the dependency of the variables. And hopefully we can use these graphical models to capture them. So for example, like if I write down the joint probability, for example, if I write down joint probability just like that, let's say if I have joint probability of X, Y, Z here, of course I can also like from this joint probability, I can derive some of this dependency among the variable. For example, from here, I can see that X and Y are independent and so on and so forth, but X and Z are independent. But it's not intuitive to look at the joint probability to try to figure out like what's independent, what may be conditionally independent and so on. So these graphical models will help you. Once you write it down, it's become like quite intuitive. What depend on each other, what does not depend on each other, and also condition on something else. Maybe like something is not depends on each other, and so on and so forth. So for the Bayesian network, it's like we are trying to have a directed graph model that to explicitly will describe the joint probability. So I will just give examples to illustrate like what I mean. For example, like I can have like x, y, z, w, like let's say, and maybe I have a directed graph model, something like that. Oh, by the way, can I have something like that?
What do you mean? Didn't understand the question.
Oh, okay. Okay, I guess I don't go that fast. Okay, this is not good. Actually, this is not okay because it's this is not cyclic. This is not acyclic because if I have something, I also have this branch here, then I form a loop. So that what we mean by cyclic. There's a cycle. So because I have a cycle, then it's not a valid Bayesian network or like valid directed acyclic graph. So now let's say I have a graphical model like that, like the Bayesian network like that. So what it means, like basically for all Bayesian networks, like once you draw write down the Bayesian network, it has a corresponding like form of like joint probability. So what this one is equivalent saying that like my joint probability x, y, z, w will be equal to px, py. Basically, we start from the root node here, like or like start from the node is not that no one is pointing at them, so that would be like they will be like just independent to one another. And then I have C here will depend on X and Y. And W, then in this case, will depend on Z, for example. So, and of course, if we can write down a joint probability like that, we can also like map it back to a Bayesian network as well. So the only thing is like you see like I should have the joint probability split into like product of like probability or conditional probability of each of the variables, like only themselves, like only one at a time. So it can be like just one where yeah. But of course, when I draw this, I also need to make sure when you write down the entire, for example, like if I put like this, it may not make sense. For example, I can have like, for example, ax given y, p y given z, p, or like, let's say pc given y, px given z. That is not valid because if you draw it out here, like this guy here, that will be like correspond to like x, y, z here. I have like from y to x, y. I should have a branch from y to x, and I have a branch from c to y, right? Sorry, y to c, right? Have a for this one, I have a branch from c to x here. So that will give me a cycle. And again, this is not valid. So I guess I will give a question that I just said, exercise. So how about I change a little bit like x, y, z, w. Maybe I have something like this. So what's the joint property? Yeah.
Can I ask something really fast?
Yes.
When you're saying pxyz, the joint probability is equal to px, py, pz given y, shouldn't that, if you expand that, isn't it px given y and pz given xy?
Oh, this one? You mean this one? This one here?
No, the
This one?
one above the graph.
Yes, this one. Okay. Yes, that's the point. Because if this I just expand that like using Bayes rule, right?
I know, but
will-
shouldn't py be given? Shouldn't py
Yes.
be py given x?
Yes, exactly. I mean, like if I just assume nothing about the variables, then according to Bayes rule, then will be like as you said, like I should have py given x, right? But here, when I draw like this corresponds to a joint probability like this. It's exactly saying that x and y are independent, basically.
Oh, okay, I got you.
Yeah. So that's it captures some of the structure of the So yeah. Okay, I guess someone write down this. Yeah. Okay.
I had another question.
Yes.
Yes. So about the triangle with XYZ. So in the equation we wrote that P. The first one is P x given y. So the direction of the equation, the direction of the graph, shouldn't it be the arrow should be pointing?
Oh, okay. I'm sorry. Yeah, you're right. You're right. That's not my intention. Yeah. Yeah, I'm sorry. Yeah, that's not my intention. I want to write something like that. Yeah.
Got it.
Yeah. So you guys have for question 2 here again, I write down the joint probability for this guy, x, y, z, w. Yeah, you can do it again. Yeah. What's the joint probability for that? Let me write it here. Maybe I'll confuse you guys otherwise. Yeah, I guess I more or less everyone got it. So yeah, that's right. So we should just have px, right? Px is not connecting to everyone, so we start with px here. Then we have py depend on x, right? pc depend on x, and then pw depend on ymc, something like that. Okay, that's good. I guess like this is pretty simple. But let's look at like okay, of course, like this using Bayesian network, what we are interested in is I look at like how things are dependent and not dependent with each other. And it's actually, honestly, it's not so obvious as you may have expected like right away. For example, like if you look at this graph here, so given W, okay, or like something we okay, maybe I shouldn't jump ahead. Maybe I start with like something really simple first. Let's say we start with like, of course, like the simplest case, like one variables that doesn't do anything. So we have two variables, right, x and y. Now x and y have like a couple cases, right? I can have x and y that either no edge between them, or I have an edge from x to y, or I have an edge from y to x. Y. Let's do the same thing. So of course, okay. I guess I give you one more question just to see like if you really get it. Or maybe I have these three different cases, right? Yeah, this may be like good for maybe let me continue first. So for xy here, I know the joint probability in this case will be what? It will be just like equal to px and py, right? And for this guy, will be equal to px and then py given x, right? And then this is like pxy would be py px given y. Okay, my question, let's say like question here, are these equal or not? Are these models equal or not? Model the same? So are these models same or not? Okay, very good. Yeah, they're the same. Note that like when I have only two variables, then not lots of like interesting we can talk about these two variables. They can either be like dependent on each other or not independent, or like independent of each other. So for these two cases here, no matter you're writing this way or writing this way, it's just ended up like this way. But if you look at that, it's just like the Bayes rule expansion, right? So this is like, this actually always hold. This is just Bayes rule. So therefore, like when we write these two here, it's basically saying that like there's no constraint on these two variables. Basically, we didn't say anything about it. Actually, they can still be independent, but we didn't specify that. But for this one here, we actually explicitly saying that these two variables are independent to one another. So okay, this is like two variables now considered like a little bit more complicated with like three variables. Again, if I have no edges here, then will be just independent, right? So I have px, py, pc here. So if I have one edge, let's say like this, I will have like p x, py given x, and pc, right? So, but this is actually basically nothing. It's like this is just base rule here. It's like just saying pxy and pc, right? So it's just saying that like this pair of variables are independent of c. So it's just saying that. And of course, you can do symmetry kind of like connection like here and there. Those will be the same cases here. So therefore, let's consider like two edges now. So if I have two edges, I can have a couple cases, right? I can have this. I can have, or maybe I put y in the middle, like let's see, x, y, z, like that. I can have like this. I can have like this one, right? I can have like this as well. And okay, so maybe just make lots of questions here. So I would say like two of the models are the same. So which two are the same? You probably want to spend more time than that. Right. Maybe I ask a related question. Which models have conditional independence among some of the variables? I'm not sure the question is clear. So what I mean is like in one of these, one or two or more of these models here, there's some conditional independence. For example, like that may be like conditional independence of x let's see. Okay. Where's that? X independent of C given Y, let's say. In some of the in couple of the models, I don't know. Which one have like conditional independence and what? So my hints for question 4 is like the answers are the same, questions 4 and for question 5. So the two models actually, yeah. I would say two of the models have conditional independence somewhere among the variables, and the two models with the conditional independence are the same. Wait a sec. Like, I guess okay. I'm not sure how you guys figure out the solution here. So you don't read the figure here, because that's the point. Like, we don't have we just, when we are learning these figures, we have no idea like what they are, right? There's no way to. So instead, you should try to write down the joint probability here, and then from the joint probability you can see whether there's any conditional independence, right? Okay, I guess yeah, I guess you want to write down actually, if you write down the joint probability, then it will be here. So let's write down the joint probability for each of them. So yeah, I guess when I say that, everyone changed the answer now. So once you write down the joint probability, it becomes more obvious, right? So this one is a py given x, right? Px py given x, pc given y, right? So and let me erase this here. And of course, I have a xy combined together. I basically pxy, right? Multiplied by pc given y here. What's non-collider? I don't know what's that. Okay. And And by base rule, like I always have like p x y p c given x y is the joint probability x y c equal to this guy, right? So it means that like from this graph itself, we are kind of like constraining like pc given xy is equal to pc given y, right? And we know where is that, what's the condition for this one. When this is equal to this guy, is saying that like, okay, if I want to, if we look at the probability of C, and if we are already given Y here, then we don't need to worry about X. So then this is actually saying that like C and X are conditionally independent given Y, right?
Can you repeat this proof again? I didn't understand.
You mean the proof for this argument here?
I mean, yeah, this arguments with both the equations and then arguments.
Okay. Well, the equation here, this is just base rule. So because you remember like base rule, okay, I guess I should, some of you like asked me like earlier. So sometimes maybe like this, the base rule you all usually see, right? Like when you first learn count probability. But typically I would like to plot the form more. It's like basically I just multiply this guy to the other side. Then also like if you do that, like you can kind of like form a kind of like a chain rule here. For example, p x y z here is equal to p x p y given x p z given x y, something like that. And the intuition is a very kind of like lateral also, like your probability would be like first the probability of x, and then like consider like probability of y, given that like x is small x here, and then like multiply by like probability of c, knowing that like x is now small x and y is small y here. And by the way, like I can also like have something xy given w will be therefore is equal, or like xyz given w. It's px given w, py given xw, pc given xy w, something like that. So anyway, like this is just base rule. So I'm just using base rule here. So this is just base rule, right? That always true basically. But at the same time, like from this guy here, from the Bayesian network, like I know that the joint probability is equal to this guy, right? And then I use base rule again, like this, I can combine together to get pxy, right? So now I compare these two form here, then I see that there's actually a constraint when I draw this figure here, this Bayesian network here. I know that like py given x has to be equal to py given x is pc given y should be equal to pc given xy, right? And this one is actually just a is a condition is equivalent to the conditional independence of x. XMC should be conditionally independent given y. Because if you think of like I given y here, then like knowing x doesn't change your probability of c, right? So it doesn't matter like what your x is going to be, then your probability is still the same, like the same thing here, right? That will be the one that does not depend on x. So therefore, like x and c must be independent, but independent only under the condition that y is given, right? Is that clear now?
Yes, yeah, I understand now.
So yeah, so therefore, like I have that. Yeah, basically the first is actually saying this, and the second one here, if I write it down here, it says p x p z p y given x z, right? So and if you compare with the joint, I mean using base rule again, like if I compare with base rule, that would be like px. I mean just pxyc. In general, if I expand, that would be like pxc py given xc, right? So now I compare these two guys here. Basically, I would just have like this is equal to this way. So it's just saying that like XMC is independent, and that's it. Yeah, basically, XMC is supposed to be independent, but I actually know that also like XMC are independent, but given that's only when let's see how do I explain that. Let's see, when you observe Y, even though XMC are independent, but when you observe Y, XMC are no longer independent. Let's see, what's the best way to? Oh yeah. So because I yeah, consider like I have like PXC given Y, right? From this to get PXC given Y. So this should be like PXYC over PY, right? And PXYC is equal to PXPC PY given XC over PY. And if this is like conditionally independent, this should be equal to PX given Y multiplied by PC given Y. Let's see. Yeah, okay. I will just say like you cannot have this is equal, right? This won't be equal basically. So and remember, like we also have like some actual example for this kind of stuff. If you remember, like you can have things as independent to start with, but Y is like depend on XMC. Like remember, like we always use the same example. Like let's say XMC like is two conflict here, like, and let's say I kind of like convert to the outcome to 0 and 1. Let's say, right, this is 0 and 1, 0 and 1, and these two events are independent. But if I have like this Y is equal to like X or like Z here, then given Y here, then these two guys will no longer be independent. So basically, I just want to emphasize that like we have here actually for this case B here, we have the case that XMC are independent, but maybe I just write here, XMC are independent, but we don't have X and Z are independent given Y. Yeah. And for the third case here, I basically have like P, Y, P, X, Z given Y, right? Let's see. And this will be like P, Y, P, X given Y, P, C given X, Y. Wait a sec. It doesn't, I guess I must be, yeah, I didn't sleep well yesterday. So Px given Y and Pc given Y. So that should be like this. Yeah, I'm sorry about that. Py, Px given Y, Pc given Y, right? Then yeah, I just combine these two. Like I have Pxy now and Pc given Y. So this is exactly the same as this one here, right? So therefore, like A and C is actually the same model here, but B is not the same. And A and C is like corresponding to, you have something like conditionally independent given another variable, but B is basically have like two variables are independent, but it's not conditionally independent given the third variable.
Is there any way to without writing these equations to figure out the independence from the model or the direction itself? Is there any way to understand?
Yes. That's why we're going through this. Yeah. So actually, if you figure out this like three variables case, you will figure out like for a larger graph basically. And by the way, like even though yeah, so therefore like just wait, you will see that you can do that. So we just say like this is equal to this way, but be careful, like this doesn't generalize when I have more variables. For example, like if I have for this one, if I also have a W here connect to this guy, you can make a different color. I say W here, and then I have W here. Then apparently these two models are not the same, because from this guy here, I have like W and X are independent, right? Because they're wood node. But here I only have W by itself. So therefore, like apparently W and X are not independent. Okay, so we look at like two.
So
yes.
In the first part, in part A,
yeah,
I have a little bit confusion. When you combine X, Y, and you have Z given Y. So how from this we come up with this condition that Z is independent of X given Y. I could not. Can you repeat this? I could not get the track of this. Yes.
I mean, like, yeah. That's actually is the condition for conditionally independent. So basically, you think of that, like what's going on here is like, actually, you can even think of this first. Maybe X and Y is equal to PX here. If that's the case, then X and Y are independent. Are you comfortable with this one?
Yes.
So this case, does just like, just you have an additional Y here. So actually maybe, yeah. And the argument is the same, right? For here, like why this is independent, Y and X are independent, because I don't care what is Y. My probability doesn't change, right? Yes. So therefore X and Y must be independent. And here is the same, like you see, like when Y is given, like I don't care what X is, like C and X will be independent, right?
Okay.
Yeah. So therefore, like I will have like X and C conditionally independent given Y.
Okay.
Yeah. So okay, and let's see, we have, let's say, consider the last case here. Last case for three variables here. I can basically just have something like this, because I cannot have a loop here, right? As we mentioned earlier, this is not okay. So if I have something like that, that's correspond to like Px, like Py given X, Pz given Xy, right? Then that's nothing. This is just space rule. So when you have like all these like three variables and they are all connected to one another, there's basically no assumption on the constraint, any constraint on the dependency or independence, or like independence and conditional independence of the variables. So so basically that's three variables. Now, like Mookie mentioned that, okay, how do we figure out when we have a more complicated graph like Y, C, W, U, let's say, V, let's say. Let me just draw whatever. something like that. Like maybe I write like this. So how do you know like something is like kind of like they depend on one another, not depend on one another? First of all, like if they are connected, like they will be depend on one another. But when they okay, they are okay, or I should say, if there's a path from one to from one end to another end, they will depend on one another. But
Is it like second one will depend on first, or it's the other way around? Like is
yes,
X depending on
but
Z?
be careful. Like yes, there's some caveat here. You mean the case B, right? He said like they okay, yeah. If I just if I don't condition on anything, then if there's no path, I shouldn't worry about that, right? So let's see. Actually, it's not always like even like this. Like you have XMC will depend on one another. So if you don't condition on everything, so if they share the same parent somehow, like if they have like same what's that ascendant, like then they will be depend on one another if we don't condition on anything, or if like one is direct descendant of another, then apparently like they will depend on each other. Is that clear? Like in this case here, XMC will depend on one another, basically. And XMC in the third case, it will depend on each other also because they share the same same ancestor. Yeah, I'm thinking like what's that word? And
in case B, they share the same child. That's why they also depend on each other, X and Z.
yes, that's the tricky part. Like X and Z here does not depend on each other if you don't condition on anything. But the tricky part is like if you condition on something, if you condition on this child here, when you say condition, it's like given. My given is like you know that. Basically, you observe that. If you observe Y here now, then X and Z depend on each other. But by themselves, if you don't know anything, then they are independent. Remember always this class example here, like this two conflict here. If these two concepts, you don't see this Y here, that is the sum of these two outcomes here, then they do not depend on each other. But once you observe this kind of like the function of these two outcomes here, then these two become dependent on one another.
Can you kindly repeat this part that for the figure B, X and Z are independent in a case, and in what circumstances X and Z are not independent?
Okay, here, X and Z like independent by themselves if you don't condition on anything, but they are not conditionally independent if you are given Y here. So if you observe the child, the difference is like where do you observe that? If you observe this Y here, now X and Z does not depend on one another. Oh, so yeah. Sorry. If you observe Y here, X and Z no longer be independent, so they depend on one another.
Can we figure this aspect out by just looking at the equation or just by the figure, that whether or not X and Z for the case of figure B are independent or not independent, just by looking at the figure or the simple equation?
Oh, I think like it's okay. Actually, what I do like usually do is I think of the simplest example here, then I generalize. That's actually easier. That's actually if you want to try to just remember rules. That's like I hate to do that. You can look for so-called D-separation. People come up with like just saying that like okay, this variable and this variable will be independent given like something else like based on like a list of rules. But actually, I think it's much easier. Like you can just look at, if you remember like this simple example here, you will figure out the rules. Because like the rule is basically something like that. If you don't conditional anything, if you don't condition anything, then the nodes will be independent, or like the nodes will depend on one another only when like one node is the descendant of the other node, or like they share the same ancestor. So if you move, kind of like move up to your like ancestor, and eventually they converge to somewhere, then like they will be dependent on one another. That's the thing. That's when like you don't have condition on anything. But once you condition on something like this, they become tricky. When you condition on something, like something is flipped. So originally, like you have like two variables, like two parents. If they share a child, if you observe that child, then they become dependent on one another. And then this can go somewhere, this can propagate, right? Because for example, if I have, let's see. For example, if I have, so to begin with, like X and Y does not depend on one another, right? Because, or like X and W does not depend on one another as well. Okay, maybe I shouldn't draw like this. I mean, these two will not depend on one another, right, apparently, because like they don't share the same ancestor somehow, right? Or like one is not the ancestor of another. But on the other hand, if I observe this, if I condition on U here, now Z and W will depend on one another, right? This is basically like by this case B there, if you remember case B is saying that like if you just look at like three variables here, if basically if they share the same, two nodes share the same child, then if they themselves will be independent, but if you observe that child, then they become they depend on one another. Now, if I observe you, yes.
What I can conclude from this is that for the case of figure B, it can be dependent and independent at the same time, given how we are observing the child.
Yes, that's exactly the point. Like that's remember like this the example that we use several times, or also like or like if you remember like we I guess I emphasized a couple of times is like be careful, like you can have like something independent but not conditionally independent, right? You both way is not correct. You don't have like if X and Y are dependent, then like you have like X and Y are conditionally independent given some variables. And also if you have this, doesn't imply like X and Y independent as well.
What would a graph look like if X and Y is always independent given anything and also not given anything?
That's it.
Oh, just not, okay, that makes sense.
Yeah, they are not connected. Yeah.
I had a question.
Yes.
Can you go to the previous page?
Yes. Is that this one or like?
No, the one where you
yes,
had five variables. Yes. So given U, are X and Y also dependent?
Yes, that's my point. Like now, because I given you, you can just do transit. The dependency is transitive, right? So now you know U and W depend on each other, and you know X and C are depend on each other. Y and W are depend on each other. So therefore, Y and X will depend on each other. So therefore, like I would say, like rather than remember the rules, is I think it's easier. Like you just think of the three very simple case, like the three nodes very simple case, ABC case ABC. Then you know that like for this special case, like with parents share child, whenever you condition this child, the parents become like depend on one another. Then you can just trace back like which node depends on this guy, which node depends on this guy, because this guy depends on this guy, so therefore this guy depends on this guy depends on this guy, so these two depends on one another. Yeah.
Is there any way to figure out by just looking at the figure that the child is being under condition or not while just looking at the figure? Because obviously if the condition is put on the child, then it makes parents dependent, and if not, then the parents are independent, provided they are not connected.
So you mean like, do you, okay, you want to change, you want to see like what you condition or what, like what you want to condition is based on the problem, right? So it's based on like what you are observing, right? You can observe this or you may not observe this. And it's and then like once you observe this, then you can figure out like whether that depends on one another, right? And of course, if you have more path of potential dependency, for example, like if I have another path like something like this, then or like maybe
in this figure are x and y.
Yes.
For the figure, if you connect z with y, will this make x and y dependent or dependent?
Yeah, x and y will be dependent on one another. Like
no, if you connect y with z.
Y and z, yeah. Do you condition on anything?
No condition on anything. So
yeah, it won't depend on one another. Yeah, x and y will not depend on one another because for them to depend on one another, like if you do not condition on anything, they has to share the same ancestor basically, or like one has to be the descendant of the other.
But they would depend on each other given z.
Yes, if given z or given u, they will depend on one another. But if you are given w here, like with this little edge here, given w, it doesn't change anything, right? Given w, it doesn't do anything. But given z, x and y will depend on one another.
Talking about that same graph without that extra line drawn in, are we also implying that x and y given z is dependent, or is it just given u?
Just given u. So xy given z does not depend on one another. So x will still be independent given z.
But if it was, what if it was xy given zw?
If xy given zw, no, it's still like it won't depend on one another. So
Okay.
actually, yes, that's and also like that's one more thing like to know about the conditional independence as well. Like we see the three cases here, right? So A, B, C cases. Like maybe I put it here also. Like that's one case here. And also like I have like one. This is a one more. So and here to begin, okay. For now, consider these two cases as well. What happened with given y for each of these cases here? Or basically, these two are the same, right? Remember, these two models are actually the same, like this. Actually, maybe I shouldn't like. Maybe I'm convinced. Yes, exactly, right. So because we mentioned that already earlier, right? We said that like for these two models, like XMC are conditionally independent given y, right? So actually, I didn't really waste. I shouldn't make it like a question because I just want to remind you guys what we mentioned earlier already, is that like given y, we show earlier that like for these two models, like this is model A and model C, right? For these two models here, given y, x and c are independent, right? So use this into kind of like just put that in our toolbox. So whenever you see that, like actually here, to begin with, like XMU here not independent, right? XMU are not independent, right? But however, if I given Z here, XMU, okay, XMU are not independent, I should write like that, are independent given Z, right? And also the same case, like same case like for this more complicated model here. Now, if I give them Y here, so originally there's like connection like between like Z and V here, right? C and V are not independent, right? Because they share the same ancestor Y here. Now, but if I give them Y here, now this path is gone. Basically, this dependency based on this path is gone. However, I still have dependency from this pathway, C to W to V, right? So, but then if I also given this guy here, I will break this path as well. So I will have like C and V are conditionally independent given Y and W. So okay, I guess you can create your own rules, like basically, but I guess all these rules is like it's just like generalization. There's several simple cases A, B, C here. Basically, your A, B, C cases also like A and C is the same thing here, right? Just B is like this different, and for A and C is like if you are given the middle variable there, you basically break the dependency. And for model B, it's actually exact opposite. You start with like independence between the two variables at the two end, but once you kind of like given the observe the middle variable, now you connect the variables at the two end. Maybe I just write it down like to summarize. So maybe I just erase all this. And then like from this, then like you can just figure out this independence and dependence, right? So if you need to have like something independence, two variables to be independent, you need to make sure like the dependency from each of the path is broken, right? Or like there's no dependency from each of the path. They are either does not exist right at the beginning, or like they're broken because of like observing some variables, right? When you are when all these paths are broken, then they will be independent of one another. So basically, we just have like two cases here, really. A and C are the same model, and for this one here, like you start with like yeah, maybe I also write it here. Maybe I write here. This model B here. So you start with like X and Z are independent, right? But if you're given the middle variable, then they are no longer independent. But this model A and C is exactly opposite. You start with something, so you start with something, this is not independent, right? But if you're kind of like observe the middle variable here, you will break the dependency there. So you have like X, C given Y. Yeah. So is that clear? So maybe like, okay, why I erase this example here? maybe I just check your understanding. UV maybe. So I don't know what's this question. What question? Six. Okay. I don't know. I'm making like maybe I can figure out myself. Even so, what? So first of all, like, is that y independent of w? And maybe one more like. Okay, maybe like this first. Is that y independent of w? Okay, yeah, that's easy, right? Yes. Okay, and is that y independent of w given u and z? Yeah, you should read more carefully. So yeah, they should be conditionally independent because yes, given u now w and c, w and y will depend one another. W and all these will be depend one another. But given c here, the dependency from here going up will be broken, right? So therefore, like given u will turn this on, turn this path on, but then given c will turn the path off again. So then break it, and then like it will conditionally independent given u and c. Yeah. So okay, I guess more or less you guys have the idea. So I guess this is for the Bayesian network. So that I like to just like kind of like explain like this dependency and independence like that you can figure out from the figure itself. So the next model we want to move on is like the.
I had a question.
Yes.
Just if you already have this plan or if time permits, can you later give us an example of question in our homework and how we can convert that data into a model? For example, coin toss and selecting a coin and then flipping coins. how we can express the relationship with this graph.
Actually, for your con model, let's say you have like P, I forgot the variable we use. I guess it's X, right? So we use X as a fifth con, and then we have Y, right? So basically say Px and then Py given X, right? So actually it's a very simple model. It's like just Y and X, right? But we have like fit multiple times. So we have Y1, Y2, right? All depend on X. Now you see the conditional independence here, right? Now Y1 and Y2 are depend on one another, right? This is actually like a model A, right? Remember, the model A is like, sorry, this is model A or model, I guess I don't quite remember. I'm sorry, like C, right? Okay, yeah, okay, this is C. So the model C themselves are not independent, right? So like Y1 and Y2 by themselves are not independent, right? Y1 is not independent, Y2. But given X here, like Y1 and Y2 are independent. That's exactly like what we had in the homework, right? So if we know the con, what that con is, then Y1 and Y2 will become independent. Yeah, is that clear?
Yes, got it. Thank you.
Okay, yeah. So okay, then we move to undirected graph. So undirected graph is, as the name suggests, is undirected. And basically just like okay, the idea is actually is simpler. Let me just write lots of variables here. Maybe C, W, something like that. So what the undirected graph is, it basically, the thing is like for undirected graph, unless you are not connecting the nodes like X, Y, if like they are not connecting, then they are independent. Otherwise, you things are all depend on each other. So for example, like if I have U and V here, then this fashion and this fashion will be independent by themselves. But everything like inside like this square, like X, Y, C, W, and also U, V here, they will depend on one another. And other things that can be modeled by the undirected graph is the conditional independence. Is if you basically, it's very simple. If you have two variables here, X and W, let's say, if you break all the path, basically, if you observe this and observe this, each time you observe something, then you break the path, basically, then they will become independent. So for example, X and W now is independent. Once I observe, so for this graph here, I have X independent of W given Y and Z. So okay, this is simple, right? Undirected graph is simple.
I had a question.
Yes.
From the graph, it's very simple that given Y the maybe the path breaks, but I don't get the intuition like what is happening. Why is the path breaking given Y for directed and undirected graph both?
Oh, you mean for the undirected graph or like for the undirected graph here? Right?
For both the graph styles, given why is the path breaking? I understand it with equations, but I don't understand it through the graph.
Okay. For the directed graph, remember that you always go back to the joint probability, right? And I don't think that you can get many intuition from the directed graph, like unless you read many graphs and saying, okay, I know that, like, as you know, right, you have like something like that, or like something like this, and you say that like if for this case here, if I observe that you break these two things here, okay, that's no intuition, right? If you, it's basically your intuition is coming from you went through like a couple of these examples, and you know that the joint probability are like this, and like for this case, it's actually happened like this. I mean, like you cannot get intuition just looking at this arrow and the pointer, how they point it. So therefore, like for directed graph, I don't think like you should even try that. Like I think you should just remember or like understand the several examples there, and then you will figure out like, okay, actually for this case here is correspond to these two are independent, and I observe this now is no longer independent. So and for this guy, like if I these are depend on each other, but I'll observe this like they are independent. So I don't think I answered your question, but I don't think like that's an answer for that one. And for undirected, again, for undirected graph, like I don't think like this is really an intuition, but it's just they are constructed. It's actually constructed in a more intuitive way. It's just saying that okay, they build a graph in such a way that like whenever I draw this graph, what I mean is like if I break that somehow by observing some variables, if I break all the path from one node to another node, then they will be independent. So this is almost like a definition of the undirected graph, basically. So did I answer your question somehow?
Yes. Yeah. Okay. I understand.
Yeah. Okay. So and by the way, there's like a theorem known as the Hammersley-Clifford Theorem. So basically, what it said is like whenever you write undirected graph, you can write whenever you can construct the undirected graph, you can correspondingly write the joint probability like PXYZW as product of the clique of the graph. So what I mean is like, for example, like in this case, there's a clique here. Is that called clique? I don't know. This is another clique, there's another clique, and this is a clique. Yeah, clique or clique? I guess it's clique, right? So and then I will be plotted each of the clique that have like the variables of the clique will be the arguments of the function. So for example, in this case, I can have this one is like phi 1, let's say. So I have phi 1 xy here, multiplied by, okay, exactly 4 color, phi 2 xz here, multiplied by phi phi yw here, and phi 4 like cw here. So I can give you a proof like this will be elaborate and like involved. But if you're interested, you can, or like it's good to know this word. Like when people say like what's Hammersley-Clifford, you know, okay, it's actually just say that like there's nothing really really very special about that. It's just saying that for undirected graph, if you can write the undirected graph, you can write the joint probability as a product of function like this. And of course, like this product in general, like may not be normalized. But we can put a normalization factor, like for example, like over by some normalization factor, something like that. Or maybe don't you see? I don't know. Maybe like squid n here, some normalization factor. And I brought it out like just because we can always say for undirected graph we can write it as like product of some function here. So an alternative representation for the undirected graph is the factor graph. That basically like we just convert this factor function into another node. For example, like here for phi 1 xy here, I just build like another node for that. So I just maybe I put a node. This is like phi 1 here, right? I put a square node here, and this phi 1 is going to connect to the random variable x and y, and I have like phi 2 here, connect to like x and c, and then I have phi phi here connects to y and w, so on, and so on and so forth. Yeah, but because of time, I think I won't go into like factor graph much. but it's good to know, okay, this is got factor graph basically. So, okay, like, and for the undirected graph, like what else I like to talk about is like, know that like for all these structure, like undirected graph, like factor graph and Bayesian networks, they are not complete in the sense like you have something like can be modeled by Bayesian networks, but cannot be modeled by undirected graph, and also vice versa. So for example, like if I consider the model, this one, let's say x, y, let's do x, c, y here, like before, x, y, z here. So this is something like you cannot model with like undirected graph, because you think of that, like what we have here is like x and c are independent, right? So x and c are independent here. But like x and c are not conditionally independent, right? Now it's I guess this is a very much when you first look at that, it's very tempting to say, okay, how about I convert this as like x, y, z, right? But the problem is, if you look at this undirected graph here, what this undirected graph represents is totally different. What it represents is like x actually depend on c, right? X and not c are not independent. But on the other hand, like x and y actually, x and c are actually conditionally independent given y. It's totally the opposite. I'm actually you cannot find a way to represent this guy with undirected graph, because whenever like you have a child share with like two parents, and you try to convert this to undirected graph, what you need to do is like you need to kind of like connect this x and c together, because know that like the undirected graph like represents like whenever we kind of given the middle variable here, if we will break the connection, right? So for this guy here, if I'm given y here for undirected graph model, if I, yeah, let me write it x. So if I give him y here, then actually this graph itself, it represents x and what is represent this guy here, right? But I want to ensure that like it doesn't create an assumption that does not appear in the original model, because the original model does not imply this way. The original model like does not imply that x and c are conditionally independent given y, right? So therefore, what we need to do is simply like just connect this guy, so that like now xm's, but even I remove this node here, x and c are still like connect to one another, so they are not conditionally independent. But of course, like if you do that, then that's raise another problem, because like, yeah. Anyway, so, but yeah.
Sorry. So the reason you connected x and z is because you wanted to represent the first graph in the second style, in the undirected graph style.
Yes.
But that doesn't fulfill the conditions, does it? Fully?
It doesn't. But know that like this is the constraint. Actually, this is the constraint. This is a basically like what I'm saying, like the constraint, if you cannot satisfy that, that's okay. But if it doesn't have a constraint, you impose a constraint, then you modify the model, right? So, or like you should consider this as assumption. No, I don't, yeah. Yeah, this is, or I can consider this as assumption. So if you don't have the assumption, you impose an additional assumption, you will make a totally wrong answer, right? But if you assume that you don't use that assumption, and turns out you can basically, it's like some kind of relaxation, right? You relax the problem, right? You don't use the assumption, you still manage to get the answer, then your answer at least is a reasonable answer, right? But on the other hand, if you really have okay, I guess I'm making like sounds more confusing than before. Well, what I want to say is basically like the independence here, like okay, I write down these two conditions like this in the same level. I mean the same amount of assumption on these two conditions here, but it's not the same actually. This is something like if you don't give it, like you will assume that's always like that is the case, right? You will always assume, okay, things is not conditionally independent. I mean something like that. And the independence is like you write it down only when that is actually happen, right? So what I mean is like if I don't have this path here, from this guy to this guy is not good, but from this to this is kind of okay. It's not perfect, but it's kind of okay. They are independent because okay, or like I should think of like this: Px z is equal to Px Pc given x. This always hold no matter what, right? This is like no matter what happened, this always hold, right? But only when this is independent, I can write it as Px Pc, right? So if I have this independence, but if I don't use this condition, so I assume this, but this is still true, right? Because even this, I have this condition here, it doesn't mean this equation is not correct. This equation is still correct, basically. But if you don't have independence and you say like Pxc is equal to Pxpc, then you immediately have something like you put in a wrong assumption, right? Same thing for the conditional independence. So if you don't have the conditionally independence, but you suddenly just like impose a new constraint for that, like conditional independence, then you can get a very wrong answer, basically. But let's say if you have the independence assumption, but you don't use the independence assumption, you get the solution that may not be independence, but it's kind of okay, actually. Yeah. So I hope I make it clear for that. And that's why like it's important that like we add this branch here, because like we don't want to impose kind of impose a constraint does not exist in the original model there. And by the way, like I guess I kind of like digress quite a bit. So actually this have a kind of interesting name for that. Like for this procedure, it's called moralization. This kind of like is an analogy, basically like if you have kind of like a child born out of wedlock, and then like you kind of like moralize the parents, just get them married, basically. Any other questions? Like, oops, I guess I spent quite a lot more time than I thought. So let's see what else I like to talk about this. Oh, actually, yeah, this is like a Bayesian network, but it's not representable by undirected graph, right? There's also another way one, like say I can have like undirected graph. Actually, this is the one we gave it before. This is like a model we cannot model using Bayesian network. So for example, if you try to model this with Bayesian network, the reasonable trial would be like something like that, right? X, Y, Z, W, right? Because like for this guy here, I have a conditional dependency, conditional independence of like X and W given Y and C, right? And also like this guy here, model this, I also have like X and is a conditionally independent of W given Y and C here. But however, like this one, because of the moralization we just mentioned, right? Whenever we try to convert this back, like think of this as a undirected graph, we should have like Y and C are connected, right? And this additional branch will just like break the conditional independence between Y and C, because from this graph here, we also supposing have another condition is Y and C are conditionally independent given X and W. But yeah, but this once we have this edge added, like with the because of the moralization, then this condition cannot hold, right? So okay, yeah, I'm sorry. I guess I because I'm watching a bit, like, but you can try to figure that out like yourself, like try to think of that, like, can you create a directed graph model for this one, like directed acyclic graph model, like to represent this guy? Then you will find that like that's impossible to do that. Basically, you cannot find a Bayesian network model that can satisfy both of these conditions here. Any questions with all this? I'm sorry, like it takes much more time than I thought. I guess we probably still should take a short break or something, maybe maybe 7 minutes until 5. Like, then we'll come back. So do you guys have any other questions on these graphical model things? If not, then when we come back, like I'll spend some time on MCMC. Like I don't think I can, again, like because of the time I have, I guess I will go pretty quick. I guess I will go pretty high level, but I guess it's still like probably worth like talking about them. Like it's something interesting. Yeah. Okay. Let's come back like at 5, I guess. Okay, I guess we'll just continue. May need to erase some of this. So so we have like give an overview of MCMC. So of course this is a Markov chain Monte Carlo. I guess I will give some motivation first. What is supposed to solve. Actually, I guess you just think of Monte Carlo first. Monte Carlo just like simulation, right? Do experiment. So you solve the problem by doing experiment, like what you did like in the first homework, and also like in the homework 5 as well. Like you that's both of them, like you can kind of estimate probability or like estimate some variables by using like simulations. So basically, like if you have a distribution like X here, so what we're trying to do is basically, let's say I'm trying to estimate some random variable, not random variable. Let's say I'm trying to estimate some outcome related to some random variable. Let's say I have px here, and then like I have some outcome like depend on x. So if I want to look at the expectation of that, like expectation fx, let's say, it's something like that, right? And so basically, I can estimate this using simulation, right? Instead of like compute this directly, I can draw samples from this P here. I can draw like sample X1 up to Xn, let's say, and approximate this guy as like Fx1 plus F, or like maybe I just use a summation sign also. I can approximate this expectation with this guy, right? Like what we did, for example, like in the homework, you're trying to approximate the probability, right? The probability itself, like in general, you can think of the probability, not in that particular problem. Let's say if I have like trying to estimate the probability of something related to X, or like maybe I directly will try to estimate Px here. But that can be approximated as like drawing from X, maybe like I write this, right? Probability X equal to hat estimated as like a kind of indicator function of like X equal to hat and sum over that and for n, right? So this is basically is equal to 1 only when X equal to hat, something like that. And for Monte Carlo in general, like you see that like you can either, I think of like two very obvious applications. One is that you can do visualization, you can draw samples, and after drawing samples, maybe you can do simulation, visualization, and so on. And the second thing is like to do like inference in the sense that you're maybe you have some as in those examples there, like in the homework, we try to find let's say, let's put it this way. So let's say like I try to estimate the probability of X somehow, right? Do the same thing, probability of X, but given the observation, right? So if I want to find what's the probability of X is equal to something, like again, I had given this observation here, then if I'm able to draw from this distribution, let's say I can, if if I'm able to draw from this distribution here, and get sample x1 up to xn here, then again I can have this indicator. Oh, sorry, this is xi here. Indicator function like xi equal to hat, like something like that, to do something like this, right? So if I do that, like it can do that, then in the sense I can do inference as well. But as you can see, like in the homework problem, it's actually pretty simple because like when we sample, like we only sample in a discrete random variable from a discrete distribution. Actually, for our case, it's even simpler, right? Because it's just a binary distribution. But in general, like if you're a continuous distribution, even in low dimension, like even for 1D, so if I have X is 1D, I have a PDF, like something like that in general, it's totally unclear how we can sample kind of like this sample data from this distribution, right? I assume this is a PDF here. So that requires us to like have some techniques to do Monte Carlo, and eventually ended up like to do something known as Markov chain Monte Carlo. So, but let's look at the simple things we can do first. Right? The simple things, like one thing is known as the rejection sampling. So basically, like Actually, in the homework, essentially what you're doing is actually a kind of special form of rejection sampling. It's like you kind of, let's say I have this PX is a PDF here, right? I don't know how to sample this. Like for example, I only know how to sample a Gaussian distribution, right? Okay, right? Or like some form of Gaussian here, right? So, but I don't know how to sample from this guy. So what we can do is like simply I scale up, sample from this Gaussian instead, but I scale this Gaussian like to cover this PX here. So what I mean is that like, let me redraw like maybe here. Oops. Yeah, maybe I draw this smaller, then I'll make it better. So I have this PX, it's okay, that's bad. So this, yeah, P is like that. So I have like, what I can sample is like this QX here, let's say QX here. And I scale this up. This is actually CQX. So CQX is bigger than PX always. Then, for example, if I sample from this guy, if I sample like QX and get a point here, get an XI here, then I will decide whether I'm going to accept this point or not if according to the ratio of this PX over CQX. So basically, accept sample with probability PX over CQX. So in the homework, like we also like, we only accept sample, like if you remember, like there's a head and tail, right? I think it's like first a head and then the second a tail. I forgot like which one which. But then like you basically reject all the sample when it's head, when it's tail, right? I'm only accept the sample like this is when it's head. And what you're doing is that actually in the same idea of the rejection, actually you can, I guess you can kind of analyze or like explain that in the form of rejection sampling completely. So yeah, you basically in that case you just reject samples whenever it's less than less than anyway. So okay. I'm sorry if that I try not to watch, but I don't know. Please interrupt me because I when I try to watch, I guess I easily get people and there's no point for me to watch honestly, but that's just like it's hard to control. So like if you find anything unclear, just interrupt me because it doesn't matter like if I can complete it or not. It's I talk about this for you guys. It's not I talk about it for myself, right? So anything you find unclear, just interrupt me anytime. So so this is rejection sampling. So the problem for rejection sampling is like especially in high dimensions, you can reject lots of samples, right? If your proposal distribution is like quite far from your okay, what we call this sample that we actually sample from is like the proposal distribution. So if the proposal distribution can be quite far from the real distribution, like in this case here, if I have the sample here, then I have a big fraction of like samples I'm going to reject. So therefore not very efficient. So a little bit kind of like an improvement is like the importance sampling. The importance sampling, however, it's not the same favor as rejection sampling. It's like not actually sample a data that is from the distribution, because if I use rejection sampling and I got the sample actually behave like the sample that we are interested, the distribution we are interested in. But for importance sampling, again, we will sample from the proposed distribution, but we'll use all the samples. And also when we look at the samples there, like because we use the samples from the proposal distribution. It doesn't look like the distribution of interest at all. But we only care about the expectation. Basically, we want to look at, let's say, compute the expectation here. So we want to compute this expectation fx, right? With x like a sample from px here. But we cannot sample from px, we can only sample from qx. So what we can do is that we just adjust that, right? Because this guy is equal to f x px, right? And but I can think of this as like x f x px qx qx, right? Something like that. So therefore, like if I sample from qx, then this expectation will be just equal to fxi pxi over qxi, something like that. I equal to 1 to n. Here is I'm assuming that I'm drawing sample like x1, xn from qx here. So if I draw sample like from qx, like to get like x1 up to xn here, I can approximate the expectation of fx with x like sample from px with this inside, basically. And this is the important sampling. And now, basically, like, because as I said, like the important sampling do not get the actual sample, right? So it is not as useful as the rejection sampling if you just think of like the actual sample you get. Like you cannot think of the sample as like the real samples that you have. So that's why, like, okay, people want to continue to improve, like how can we do sampling like that can sample from like any distribution and still like the sample like will be like the original distribution. Like apparently it's not easy like for us to sample from any distributions. So basically the idea of Markov chain Monte Carlo is, I guess I may need to mention a little bit more like what is Markov chain again. Like of course I think at this time like you know that okay, Markov chain is something like that, right? Pxn xn minus 1 xn minus 2, so something like that. X1 is equal to xn given x n minus 1. So you can think of a Markov chain. So yeah, I know that like we use Markov chain like XYZ and XYZW and so on, like we mentioned like that. But when we think of the variables are in a time sequence, the Markov chain basically is just saying that like the current states will only depend on the previous states or like I shouldn't say only depend, but given the previous states, it doesn't actually depend on the earlier state anymore. So therefore, like you can really think of like the Markov chain itself, like when you have or actually like I guess a Markov process may be a better terminology. So it's really a kind of stochastic state model. So for example, like let's think of like we in homework 1, so we have this rainy day and sunny day, right? So we have like can represent in the, I guess, a rainy day, sunny day, like 2 states, right? And then we have transition like from one state to another, right? And I'm also like it may stay in sunny and like stay in rainy. And the stochastic state model can be all captured by this state transition diagram here, right? So you can use, I can basically represent the Markov chain using this state diagram. But okay, be very careful though of like, know that like each of these nodes are states and not x1, x2 and so on. And I'm not to be confused with like graphical model we talked about earlier also. And for this state model here, let's see. If you remember, okay, if you remember what's going on is like, okay, for any kind of like this state model, but actually it's not any, maybe I should give the condition, but yeah, I will very high level to mention that, but I won't go into detail. If the Markov chain, or like think of this Markov model, is irreducible and also like aperiodic, then no matter like what is the original state of the model, it will eventually converge to a steady state. So meaning that like if you let this model to run for a long period of time, then eventually the probability of any state, like for example, probability of this state here, will be approximately equal to the steady state probability. Meaning that, for example, like if I have after a long time t, if I sample like for a period of time, like let's say like sum over like this, let's say if I sample from this guy here, I have like x1 xi, right, xt plus 1 xt plus n, let's say. After like I kind of let this model run for like a long period of time t here, and I look at a period of this, I mean look at a segment of this sample here, xt1 up to xtn here. So I will have like about a fraction of like PR, that's the, okay, like P log R will in state R basically out of this guy here, like about P log R, this is the steady state probability here, that will be in state R, and also like have like P log S here will be in state S here. Or maybe I can write like X I X I equal to R, right? N I equal to T plus 1 to N will be approximately equal to P or R, something like that. And that's the how the MCMC work is like. Okay, you see, like it's not easy to sample any distribution, right? But what we can do is like maybe we can construct a Markov chain or a Markov model, or just let it run, and run for a long period of time, then it reach more or less steady state probability. And then like after it actually for this long period of time is long as burn-in. So it's like after a while, like it reached like more or less the steady state. Then the samples there like will behave like this steady state probability. So what this steady state probability is basically the distribution that we want to draw a sample from. So think of like what okay, maybe I repeat this again. So what we are given is basically we are given like some distribution we want to sample, right? Like let me just use P0 here. This is like what we want to sample. So want to sample from, but we don't know how to, right? Now we will just construct a Markov chain such that like P0 are the steady state probability, and then let this model run for a while, like that, let it burn in. After it burn in, then you draw sample from this Markov chain, will have sample like behave like the distribution that you wanted. Of course, like, there's a little catch here, like because apparently like samples like from this Markov chain is highly correlated. Like because like for example, if I have like this simple like rainy sunny day, right? If I have sunny, like if you remember, you keep sunny for a long time. So adjacent samples can be quite correlated. So what in practice like people can do is like they can skip some of the samples. For example, if I draw here like n samples here, maybe I would just use like every 10 samples, something like that. So then the remaining question is like, how do we start with like any kind of like distribution? I can create a Markov chain such that like I draw a sample from that Markov chain, I will get the steady state probability is actually equal to the desired distribution. So, oh, okay. I really should ask some question, but I don't know what question I can ask. I guess I probably like, I don't know, like, okay, maybe, let's see. Maybe I just ask something if you remember. So let's say if I have the transition probability from state R to state S as I Q R to S, let's see, yeah, R to S, and this is a S to R like Q R to S to R here, and then I the steady state probability here. I don't know, it's like question 7 or something like that. It's not a very good question, but I guess I just want to see if you guys are still here. So can you write down the detailed balance equation? I guess we mentioned that like in one of the class like before. So if this are the steady state probability, it will satisfy some detailed balance equation. Still remember like what was the detailed balance equation? Yeah, I just hope that still like some of you guys are here. Is my question clear? Do you remember like, so it's like relating to these 4 terms here, like remember like the detailed balance equation? Yes, that's good. Okay, at least I know like some of you guys are still here. So yeah, yes, I'm this is actually reasonable for the detailed balance equation. What it did is just saying that, right, if this is the steady state, you think of like again, like imagine like you have some probability flux that moving around. So in the next time step, after the next time step, you hopefully like you don't have no change of the amount of like probability here and probability here, right? So therefore, like stuff coming in should be equal to stuff going out. So if you look at a pair of nodes here, if the stuff going in and stuff going out is the same, then that probability is not going to change, right? So therefore, the detailed balance equation to satisfy like what Sale like put down there, or like, yeah. So so okay, that's a big hint there. So how do we construct, like, now again, like we have let's say we have the Markov chain here, whatever, given this guy, right? Of course, here I draw it like only 2 states. I can have many states here. And then for each state, they have a transition probability, right? And this transition probability, like, is something that you're able to sample, right? So therefore, like, that's no promise that, like, this guy, this static, I mean, this the detailed balance equation you just put down will be satisfied. So think of like this Q is like something we want to sample, but this guy, like, that's by no means that, like, we may have this whatever, like Q S given R times P not R is equal to P not S Q R given S. So this in general will not hold, because like this is like you sample and you sample, that's not of constraint like how you are able to sample. And this is like given from your problem, like the distribution you want to sample, and there's no way that in general this will be equal. So, but we want to make it equal, right? So so how do we do that? So think of like this, like assume that let's see. Let's see. Yeah, okay. Let's assume like this. So assume that like these are not equal. So without loss of generality, let me assume that like one side is larger than the other side, right? So I have this guy is larger than this side here. So what I can do is I can try to compensate this probability flux by saying, okay, so because like this side, so from this one, maybe I can draw like, so now this one is thicker, right? This one to this side is like larger than this side here, right? So what I can do is maybe I can reduce the probability like going out from this one here, right? From R to S, and just keep the probability from S to R is the same, right? So what I can do is I simply trying to do is if I have from R to S, I will have like P log, let's see. Yeah, the probability going out will be what's that word for that? Will be mitigate somehow by just by ratio. So from this one out to S here. So when I decide, for example, I sample when I stay out here. Now I sample and I know that I need to go to S, but I will kind of reduce this flow a little bit, like in the sense I know it's going to S, but now I won't always let it go to S. Sometimes I will block the transition there. So and the amount of the transition I should block should be just the ratio, right? So therefore, like I will say with probability this is with probability. So, and for S to R, I don't need to do anything basically. So, and actually, if you combine this together, you can just in general, you can create a rule, something like, I will be basically always, if I do the transition from state X to Y, let's say state X to Y, if I at state X here, and I sample from my distribution Q here and ended up like to go to Y, but I don't always transit. I transit with the probability of minimum 1 P0 Y P wait a sec, maybe I made a mistake here. I think I made a mistake here. SPS this wait a sec, is that way? Yeah, I think it's right. It's okay. Oh, so yeah, okay. It looks okay. Y then maybe this should be X. Let's see, X or Y. Yeah, Y is right. Y. P X given Y P X P Y given X. Okay, I should use Q here. Yeah. Yes. So basically, if you use this rule, then you can always guarantee that the beta balance equation is satisfied. So therefore, like if you continue to do this experiment, to do this simulation, eventually it will converge to the steady state probability equal to this PCO and PCO, that's the desired probability. And by the way, this algorithm is shown at the Metropolis-Hastings algorithm. So it's a classic like MCMC algorithm. And yes. Oh, actually, I suddenly I think I'm going faster than I thought. So I guess I can slow down. I don't know. So we talk about Metropolis-Hastings, and oh, by the way, like if maybe do one example here. Actually, this is not. I mean, I guess I don't need to. Not really an example, but just saying like an application, like for example, like how to connect to what we did earlier. So for example, like if for example, we have this head tail question or something like that. What's the probability of heads like given the tail and so on? Oh, actually, this one may not be a extremely good example, but let's see. Let's write like X given observation, right? Something like that, right? So in general, like we always encounter problem like that. Like we want to look at the posterior probability. We want to sample from the posterior probability. There's some latent variable, unknown variable, like hidden variable, no matter how you call that, that you want to estimate and given some observation. But typically, like the distribution that you are given, like it's not the posterior, it's the likelihood and also the pi array. So, but you know that like this is like actually this guy is proportional. This guy, right, is proportional to the multiple of this pi multiplied by the likelihood. And actually, if you want to do, let's say, sampling for this unknown variable, for example, you make the observation now. For example, like again, like think of like you observe. Okay, again, I use this head or tail. Like you observe tail. Now this x here may be is the outcome of the lexicon supposed to be, like it can be head or tail or something like that. And in general, like you are not given that, but you're given the yeah, I guess this example may not be very nice. If I use the same example that we used in the homework, then this will be like whether it's like con A or con B, right? So yeah, okay. Maybe I just used exactly example. This observation is tail, right? And this is like x here, like whether it's like con A or con B, right? So given this observation, I'm going to draw the probability. So basically, if I'm able to draw this thing here, first of all, I think of like what we are drawing here. So if we have oscillation, and I'm going to draw from this posterior distribution, I should get the outcome either A or B, something like that. And I may get like A, B, for example, like just like maybe two more or like two more. So I have like 6A and 4B. Then in that case, I can approximate, given this observation, I can approximate. If I'm able to draw from this distribution there, then I'm able to approximate what's the probability of that con supposed to be A or B, right? And that probability is simply, in this case, will be just equal to, okay, it's super stupid question. I just make sure you guys are still here. What's the probability? Is that question 8? I don't know why question 8. Question 9 maybe. Yeah. So given this very stupid things, like let's say, if I yeah. So I just want to make sure that you guys are here. So then you see, like it's really nice, right? This is like exactly like you can do brainless inference. Basically, if you're able to sample this posterior, you don't need to do anything, right? And then you can approximate the answer right away. But of course, like what you're given, like remember in the questions also, like you're always given is the pi distribution and also the likelihood function, right? Something like that. But I know this is proportional to one another. I mean, this is like the posterior is just proportional to this guy. And then I'm actually more precise, it will be equal to this over the observation, right? Now I may call this maybe big px or something like that. Now if then to sample this using like Metropolis-Hastings, I can simply substitute this guy into this one here, right? Or like into this one here. So if I'm able to sample, let's say, this proposal distribution, for example, like in this case, I only have like con A and con B, right? So I have a transition probability like A to B and B to A, right? And maybe like you just make it up, this is 0.6, 0.4 or whatever, like a transition probability. Then I will have, or like I can even make 0.5, 0.5, I don't know. And this is basically the, maybe I just make it 0.5, 0.5, 0.5, 0.5, this is QA, QB given A, and this is QA, A given B, right? And if they are equal, then this will just got cancelled, right? And then the remaining, like this part here, I can just substitute this P here inside this one, and this script P here is just equal to this guy here. So, and therefore it's just equal to you see, like observation will just cancel, right? So therefore it's just P of observation given let's say if I transit from A to B, B to A to B here, A to B here. So it will be like just observation B, PB, P observation, APA. And of course, with this probability, something like that, probability 1 with this probability to transit. So, okay. Okay, I guess I hopefully I motivate you guys that we can use this to do inference. I guess I have like less than 4 or 5 minutes. I guess I would just like very quickly like mention like what's a Hamiltonian Markov. So let's see. Maybe I will just use the same picture here. So think of like we do like what we did here for MCMC using Metropolis-Hastings. When we do transition probability here, of course, for this particular example, it's making really simple. Right? We're taking a very simple example, but usually, like a more realistic example is like is continuous. So you have like continuous state from one continuous state to another continuous state, right? And to decide like where you go, like for example, like you from this state here, x0 to the new state x1 here. Typically what you do is like we don't have a good idea like where we should go, at least like according to Metropolis-Hastings. Then we'll just like do a random walk, right? So we have a proposal saying, okay, let's try to move that and decide like, whether we should move that or not. So therefore, like using this Metropolis-Hastings, like it's like a random walk, like it's like a little bit like kind of random. So if you think of that, like we may be like a little bit stupid because like, do I really need random walk? Because like we know the PDF like pretty precisely, right? For example, like we know the PDF, for example, consider like I draw a level chart, level graph of the PDF. Let's say like this, right? This is a PDF. So if I'm, let's say if I'm here, and let's say this is the peak, like whatever. So moving in this direction may not be very nice, right? So I know this is I'll decrease the probability quite a bit, right? But because it's random walk, I will have like equal likely to go to this direction or like this direction and so on. So for the idea of a Hamiltonian Markov, I won't have time really to go into that, but just give you an idea like what it does. Hamiltonian Monte Carlo. So what it does is like we consider as a physics problem now. So consider as a physics problem, then we think of like this this probability like as like different energy level. So think of particle like you learn in a kind of like high school physics or like college physics. So when you're in higher energy, like this less likely to be there, right? So and so forth, right? So you have this Boltzmann distribution. Let's say I can map a probability into energy. So I can write the, for example, if I have px, I can write the probability like in some form as like e to log px or something like that, and consider this as the energy or something like that. And probably we want to put the minus sign somewhere. So just by the convention, like higher energy is less likely or something like that. But the point is like once we make up the energy, then we can kind of use some kind of like physics, I mean from mechanics, I actually more precise Hamiltonian mechanics, to kind of derive a deterministic equation for how this particle is supposed to move. And basically like you okay, the idea is like we have the energy here, and we expect the energy to be conserved. So we have like the conservation of energy, let's say the energy. And you know, like from high school physics, that like my energy will combine of this potential energy that will correspond to this term here, the original probability here, will be like the potential energy. It depends on like the actual location of your sample. And then like also the kinetic energy, that would only depend on the momentum, or like basically the velocity times mass here. And with that, like so usually like they will call this a Hamiltonian. So and because the energy is supposed to conserve, so if you take the total derivative of the energy, this should be goes to zero, right? And but you can make it a partial derivative like this. Hx is a function of x, and also the momentum. I will introduce a dummy variable momentum here, and then I will have like can split into like partial h partial x dx dt and partial h partial p dp dt, and this is supposed to be zero, right? So how to make it zero? I can make this to be equal to negative, let's say, I forgot which way, but that's fine. Partial h partial p, and let's say this is equal to partial x, partial h partial x. So see, if this guy, sorry. Yeah, it's okay. I don't think I have time to get into this detail. So let's just say like, so I can, high level, like I can use this Hamiltonian mechanics, then I can have a deterministically design like how the particles go. So then instead like doing random walk, I'll just like do a physics simulations and like it just go like according to physics. And from there, like I will know the dx dt, basically how it changed with time, and I mean how the location changed with time and how the momentum changed with time. And then like I can just approximate the next step. Therefore, let's say I know this guy here, then my next step like x n plus 1 will be just equal to xn plus dx dt plus some delta, right? Something like that. Then I can just do this. This is like a numerical integral. Like I can each time iterate a small step. I repeat many times for both like the location and all the momentum. So then I can like from one point jump to another point. Like they call this a leapfrog integration. So you can jump around like that. But this jump is basically deterministic, like instead of like random walk. And also the nice thing is like it's not Newton's method. Newton's method is trying here like we it's exactly doing simulation like for actually think of this is really like a valley, like this is energy like going down. So you have this particle like you have some initial momentum now. Now you do a simulation like a one, something like that. So and you can divide the equations using like the mechanics basically. Here I don't have time to go into detail, but you will have a deterministic one, right? But however, like this and also like this one, by the way, like will always be, yeah, maybe I'll just forget about that. That's fine, I guess. Let's see what else I'd like to talk about that. Yes, maybe I just mention one more thing. Like some of you guys mentioned last year, the no U-turn sampling. So actually, it's a special case of Hamiltonian Monte Carlo. So because like when you do like this Hamiltonian Monte Carlo, like what we did here, you see like I have this delta t here, right? I move like each time like how far I go, like what's the time step there, and also like how many steps I run, right? And so for example, like if I run too far, then I will eventually go back, right? For example, like if I go, I iterate, like for example, like each time is like delta t is equal to 0.01, and I run it 100 times, and then I will do. Or maybe I use different color. And I may go back, actually go back to here, and if I keep on going back, like maybe I start from here or go back to here, I will just have sample nearby. It's not good. So no U-turns, the idea is like, I don't want it to go back. I want to just go to the extremum here, and just next time I also go to extremum. And basically I want to like estimate first where's the extremum there. Like if I estimate is here, then I would just say, okay, I know the extremum here, I better get samples like in the middle, like several samples in the middle. And again, maybe I go to next extremum here, and then I get samples, like some samples in the middle, and so on. And the way to figure out whether you go to U-turn or not, you can just look at the momentum, right? Because the momentum tells you the velocity, the direction of the velocity. So basically, like if you simulate in both like forward and backward way, like you have like, if you simulate forward, you have x plus here, backward has x minus here, and you check the sign like x plus and x minus, and multiply with the momentum. You want this to stay positive, otherwise it will be U-turn, right? And if you turn, then you just okay, you should stop basically. So that's basically the idea of no U-turn sampling. So I guess it's a bit yeah, because we don't have enough time. So okay, I guess yeah, that's any other questions? And by yeah, again, like don't be late for your final project, and also like be sure to look at the rubric, like the requirement, like for the report and so on. And by the way, like if you have time, like this time, I guess I'm interested to see you guys like the evaluation, because like this is like quite different like from what we did in the past, and I really kind of interested to see like how we can improve, or like how things is not doing. It's kind of like how what is good or what is bad. So yeah, if you have time, like please try to fill evaluation as well. So I guess this is not complete, but I am already over time. So I guess at least I mentioned not that like some of you mentioned. And if you want to go more detail, like you can go to the textbook by Mackay. It has a pretty good description of like Hamiltonian Markov Monte Carlo, and I guess that's it. Yeah. So, any questions or comments? Okay, I guess good luck for your exam then, and hopefully see you guys in future classes. So, or like I don't know, general exam or whatever. So and oh, I'm yeah. Feel free to contact me like with anything. I'm actually I will keep the. I don't think I will shut down the Discord. I guess I will make it permanent. So if in the future you still have something like interesting to write, I probably will use the same Discord like for the next time offer this class or something like that. I'm thinking. So anyway, like if you want to drop a message and like have any questions that you want to ask, you can ask me there also. Like, yeah, you can send me email, but sometimes I miss that. Yeah. So okay, I will see you guys then. Yeah. So good luck with everything and take care. Thanks all. Thank you all.